Hello, pre-calculus students. This is Mr. Hazelhorse coming to you live from Tuesday. Wrap your minds around that one. Today we're going to continue our conversation about limits. And before we do that, I first want to remind you of the definition that we gave on day 1 of chapter 12 here. We said if f of x becomes arbitrarily close to a unique number as x approaches some constant from either side, right? And that's what we want to keep in mind today, that x is approaching that constant from both the left and right side, then the limit of f of x will approach that value as we thought about looking at the graph. All right, so that's what we want to keep in mind as we work today. And so today what we're going to focus on are what are known as one-sided limits. So here you have the definition of one-sided limits. All right, when we talk about a one-sided limit, it's exactly that. We're going to approach that number from either the left side specifically or the right side specifically. All right? And so here you can see some notation on how we can write that. So let's kind of focus in on this notation right here to begin with. Let's talk about our limit notation from the left. So you can see it looks very similar to what we looked at the other day. The only difference you see is underneath that limit, you'll see the limit as x approaches c, and then we want to approach that now from the left. So we're coming from the negative side of that limit when we look there. All right? You'll notice down here in the limit from the right, we have the same notation, but instead of coming from the negative side, we're coming from the positive direction, or we could think of that as coming at it from the right. Right? So that's some notation that we want to keep in mind as we talk about these one-sided limits. Now, again, we can use one-sided limits to help us as we determine whether or not a limit really exists, and we can see that here again. Thinking back to that definition, if f is a function and c and l are real numbers, then the limit as x approaches c of f of x is equal to l if and only if both the left and right limits exist and are equal to the same value. All right, so that's what we want to keep in mind as we think about limits today, is we're going to think about approaching them from the left side and from the right side. All right? So let's take a look at an example problem where looking at the left and right limits can help us determine, first off, whether or not the limit exists, and if it does, what that limit actually is. So the most common situation where we use left and right limits is in the, excuse me, in dealing with piecewise functions like we have here. So we want to find the limit as x approaches 1, and you can see the piecewise function that we have established there. Now, the thing to note is that the number 1 is also kind of serving as that boundary between where we shift from graph number 1 to graph number 2. All right? So kind of keep that in mind as we go. So the first thing that we want to do is we want to evaluate the limit as x approaches the number 1 from the left side. So I'm going to put a little negative sign up there. Now, if I come at x from the left side, I'm looking at the values where x is smaller than 1. So based on the inequality here, we're going to use the first function. All right, the first function applies when x is less than 1, right? When we're on the left side or the lower side of 1. So we're going to find the limit as x approaches 1 from the left of the function 4 minus x. I apologize for my handwriting here. Not very good writing with these stylus. But anyway, so if we go ahead and use direct substitution in this setting, all right, this is then going to be equal to 4 minus 1. So the limit from the left would be 3. All right? So now let's look at the limit from the right, and hopefully let's look at the limit from the right, and again, hopefully, things will match up here. So we're going to find the limit as x approaches 1 from the right side, from the positive side. And again, since we're coming at it from the right, we need to use the function where x is greater than 1. So now we're looking at the function 4x minus x squared. So again, we'll use direct substitution here. So we end up with 4 times the quantity 1 minus the quantity 1 squared, which would then be equal to 3. And what we want to notice here is that it doesn't matter whether I come at this function from the left or from the right, right? They both exist, and they're the same value. So what that tells us then is the limit as x approaches 1 of this piecewise function is 3. All right? Let's take a look at another situation where left and right limits could be helpful. So here we have another example of another piecewise function. Again, we want to evaluate this as we are approaching x, or as x approaches 2. All right? So again, let's apply those left and right limits. So if we take the limit All right, let's try this again. All right, let's try this again. So we have another piecewise function. Again, we want to find the limit as x approaches 2. So let's approach 2 from the left side to start and evaluate the limit there. So the limit as x approaches 2 from the left. And my stylus is not working very well here. All right. So if I'm going to approach 2 from the left, I'm coming at 2 from the lower side of 2, a number smaller than 2. So if I look back at my piecewise function, I need to determine, okay, which function is going to apply there. So in this case, we're going to apply the middle function. All right, now if I notice here, the middle function is really just a constant. So the limit as x approaches 2 from the left of 10, well, it doesn't matter. I don't really have anything to substitute in there, so my limit will be 10 as I come at this piecewise function from the left side of 2. So if we come at this function from the right side of 2, well, let's see what that looks like. So the limit as x approaches 2 from the right. Well, if I approach 2 from the right, all right, we're using the bottom function. And that's just, again, a constant of 12, so this time it's equal to 12. And what we want to notice here is that our two limit values are different as we come at this function from the left side and the right side. And so in the immortal words of the Mean Girls movie, all right, the limit does not exist. All right? Because, again, two different values. So here's another example where evaluating limits from both the left and right side are going to help us determine, first off, whether or not the limit exists and what its value would be. So here we're finding the limit as x approaches 0, the function, the absolute value of 2x quantity divided by x. So let's take a look at both the left and right limits and think about what's going to happen here. All right. So let's start out with the limit as x approaches 0 from the left, which would be the negative side here. And again, we're evaluating that of the function 2x over x, absolute value of 2x over x. So if we think about what happens here, if we use direct substitution, obviously we're going to run into a problem since the denominator would be 0, this function would be undefined, but we can kind of think about what's going to happen here, right? Let's say we just started plugging in a bunch of numbers on the left side of 0, all right? It doesn't matter what negative number you pick, all right? Let's say we plugged in a -1, all right? Well, if we plug that into this function, we can see we're going to end up with 2 over -1, all right? If I plugged in a -2, I'd end up with a 4 over -2, which would reduce down. And no matter what happens, no matter what value I pick to plug in from the left side of this value of 0, we're going to see that x ultimately cancels out, but what we're left with is a -2. Right? Now let's look about what's going to happen to this function as we approach it from the right. So if we find the limit as x approaches 0 from the right of the function 2x, absolute value 2x over x. Right, well, if we come at this function from the right side, again, the same idea here, now we're going to use all positive values. But again, ultimately, whatever value we plug in for x is going to cancel out, and we're left with a +2. So the situation that we run into here, again, is a situation where the limit does not exist. Because as we approach this function from the left side, it approaches a -2. As we approach it from the right, it's a +2. we don't have a limit that's existing. And we can verify this if we look at the graph of this function. So let me pull up the graph. So here you can see the graph of this function. And again, as we approach as we approach 0 from the left side, all right, well, we can see here, right, the y value is -2, that graph. And as we approach 0 from the right side, we get a completely different value. All right, again, looking graphically, we can verify that, yes, this is a situation where the limit does not exist. But we can see how those left and right limits help us see that as well. All right? So that's the idea of left and right limits. What I want to talk about next is kind of a concept that we'll build off of over the next couple of days. So to finish out, we're going to talk about the difference quotient, which you can see involves a limit. All right? And so we're going to find the limit as h approaches 0 of the quantity f of x plus h minus f of x all over h. Right? Now, this is a function that we're going to use to set up some different things over the course of the next couple of days. And so we'll start to work with this difference quotient quite a bit. So today we just really want to focus on the algebra mechanics of how do we use this function. And later on, we'll talk about what does it mean, what do we use it for, that sort of thing. All right? But the thing that I want you to make note of here is in its beginning form, right, as we see it written right here, right, the difference quotient is always going to produce the indeterminate form of 0 over 0. All right? So think about if we use direct substitution in that difference quotient. So if we plug 0 in for h, all right, well, what's that going to mean up here? Well, if I plug 0 in for h in my numerator, what I end up with is just simply f of x, because x plus 0 is just x, f of x minus f of x. Well, f of x minus f of x is 0. And if we plug 0 in for h, we get over 0. So again, we're always going to end up with this indeterminate form of 0 over 0. So you might be thinking, well, what in the heck can we even use this for if it's always going to be 0 over 0? Well, this is where our algebra skills kick in. This is what we want to focus on today, is you're going to see if we simplify some things down, even though originally it may start out as 0 over 0, by simplifying it, we can use direct substitution to actually come up with a value that works. So let's take a look at an example problem using our difference quotient. So here's our example. We want to take the function that's defined by f of x equal to x squared minus 1, and we want to find the limit as h approaches 0 of that, again, difference quotient. Now, again, we can see if we plug 0 into the actual difference quotient, we're going to run into some issues, all right? But let's go through the algebra mechanics here, and I'm going to apologize in advance for my handwriting. I know it's going to get a little sloppy. So first off, let's just set this up algebraically. So we're going to find the limit as h approaches 0 of f of x plus h. So that means I need to take the quantity x plus h and plug it into f of x for x. So this is then going to become x this is going to become x plus h quantity squared, plugging x plus h in for x, minus 1. And then we're going to subtract from that just f of x, which would be the quantity x squared minus 1. And all of this will be over h. So if we simplify things down here, right, let's go ahead and multiply out our binomial here, and we'll do the algebra work. So we're going to end up with x squared plus 2xh plus h squared minus 1. Then I'm going to go ahead and distribute this negative sign through, so we end up with minus x squared plus 1, and this is all over h. And again, we got our limit hanging out here, so we're finding the limit as h approaches 0 of this quantity. All right? Now, once we have this set up, we can see some nice things happen here. So we can see that the h squareds are going to cancel. Or excuse me, not the h squareds, take that back. All right, let's go, x squareds are going to cancel, and the 1s are going to cancel. All right, so again, apologize for my blunder here. So at this point, we have the limit as h approaches 0 of the quantity 2xh plus h squared all over h. Right now, again, we still run into the problem that we can't use direct substitution. We're still going to end up with 0 in the denominator, but we can obviously see, all right, h is going to factor out of the numerator, and then we can cancel that out in the denominator. So ultimately, we end up here with the limit as h approaches 0 of the quantity 2x plus h. And now I can apply that direct substitution. So the limit as h approaches 0 of the quantity 2x plus h using direct substitution, plugging 0 in for h, is just simply equal to 2x. All right? So that's the difference quotient. That's just a lot of algebra work. Again, we're just plugging in the quantity x plus h into our function to begin with, right? Simplifying things down, getting it to the point where we can actually apply direct substitution. And then we've found our limit as h approaches 0 of the difference quotient. And so in this problem, that's 2x. And you're going to get some practice with that today on your homework assignment. All right? So here's your homework assignment for today. You'll get some practice working with one-sided limits and also some practice working with that difference quotient. I just want to let you know this video is posted on my classroom website. So if you have any questions over anything that you do in your homework assignment today, you want to rewatch the video, feel free to access that again through my classroom website. And if you have any major questions, save those for tomorrow, and we'll be back and happy to help you then. All right, everybody have a great day, and I'll see you on Thursday.
Made with Doodlecast Pro.